So I want to finish up this chapter by discussing how to find the roots of a complex number. Using de Moivre's theorem, we were able to find the power of a complex number pretty efficiently. And finding the root of a complex number is a very similar process. If I ask you to find the cube root of some complex number like z, this is equivalent to raising that z value to the 1 over 3 or 1/3 power. And so that's effectively all we're doing here when we're applying de Moivre's theorem. When we're finding a particular root, so for example, if we're finding the cube root of a complex number, that's equivalent to raising that complex number to the 1/3 power. And so we use de Moivre's theorem then in the same way that we would raise z to the n power, and we're now raising it to z to the 1 over n power. So if we expand out our complex number that's written in trig form, that means we take our modulus and we also raise it to the 1 over n power. And then we're going to multiply theta by 1 over n as well. But wait, there's an additional component to this as well. There's this part right over here. And the reason for this is because when we are finding roots of complex numbers, we are going to be finding a number of unique and distinct roots. And so if we just completely neglected the part that I have highlighted in green right now, we would just find one single root. But there may be a certain number of distinct roots. So if we're finding the cube root of a complex number, that means there could be up to 3 unique complex roots for that. And this part that I have highlighted in green allows us to move around the unit circle to find the other roots that would satisfy that complex number. So I think this will make more sense if I actually just show you this within a problem, and then visually, if I can show you what these roots look like graphically, I think that'll hopefully really hammer this home. So let's take a look at this complex number, 2 minus 2i root 3. And we are going to find the cube roots of this complex number. So hopefully we should be able to find 3 distinct roots to this. The first step that we're going to want to do here, if we're going to work with de Moivre's theorem, then we want to write this complex number in trigonometric or polar form. So the first step is to rewrite this in trig form. Put it in trig form. Okay? So in other words, we need to find 2 things. We need to find r, and we need to find r theta. Okay? So let's make sure we understand where our complex number is, because that's going to be beneficial when we are finding our direction angle. Our complex number is, our real number is 2, and our imaginary number is -2 root 3. That's somewhere here on the imaginary axis. So our complex number is somewhere down here in quadrant 4. So let's find r. R is simply, again, using the direction or the distance formula, we would say our horizontal component, 2 squared, plus -2 root 3 squared. So if we expand that out, we got 4 plus, that would be 4 times 3, so that's 12. And that gives us a nice clean square number. So root 16, that would give us 4. So our modulus, or our distance, or our magnitude, however you want to describe it, is 4. Now let's find theta. We know that theta is going to be the arctangent of our vertical over our horizontal, y over x. So -2 root 3 over 2. And that would then give us arctangent of this value, -√3, just to simplify this. And you don't need a calculator for that. Hopefully you know that means theta is equal to, in this case, -pi/3. Well, that's what the arctangent would give. However, we want to express our angle as an angle from 0 to 2 pi. So that's pretty easy to do. We're just going to express this -pi/3. We're just going to add 2 pi over it to write this as 5 pi/3. So that way theta is between 0 and 2 pi. Okay, so we're expressing an angle between 0 and 2 pi. So we found our modulus, we found our angle theta, so now we're ready to write this in polar form. So we can say this complex number z is the following. We can just write that using abbreviated form, 4 CIS 5 pi/3. Now that we've written this number in polar form, we're now going to find the cube root of it. In other words, we're going to say, okay, z to the 1/3 is equal to the cube root of 4, our modulus. And then we're going to do now that n value, which is 1/3, times our first angle, 5 pi over 3. And that is going to give us, and then we're going to keep in mind that we want to find any additional angles as well. So this is going to give us our first angle. Let me actually just pause here. So this is our first angle, just because I don't want to get too far ahead of ourselves. So this is going to be the cube root of 4. So I'm just going to write this as 4 to the 1/3 CIS, and this is 5 pi over 9, okay? And I'm going to label this here. This is our first root here. And let me actually just highlight this in blue just to make sure that we understand this is our first root. Now, if I completely ignore this part that I have highlighted in green right now, we would stop there and we would think that there is just one root to this. But this is our first root, but there can be up to 3 possible roots. So how do we find the other ones? So let's switch colors now. So how do we find the other roots? Let's find the second root now, if it exists. The second root then would be 4 to the 1/3 still, CIS, and we're still going to have 1/3 times 5 pi over 3. That's going to be kind of our basis, if you were, or our base. But now what we're doing is we're adding 1/3 times 2 pi k, where k is going to be equal to 1 here. So I'm going to just replace that k for just 1. Okay, so that's just effectively just 2 pi. So to clean this up, this is 4 to the 1/3 CIS, and we have 5 pi over 9 plus 2 pi over 3, which I'm just going to now rewrite 2 pi over 3 so it has the same denominator and it's easier to work with. So we're just going to write this as times 3, that's 6 pi over 9. And so our second root is going to be 4 to the 1/3 CIS, that 3 looks not great, 11 pi over 9. There's our second root. Since we're finding the cube root, it's possible that we have up to 3 roots, and we should have 3 unique roots. So what is our third root? And we're going to do this in order. So 4 to the 1/3 again, CIS. Now this time we're going to take, again, our 5 pi over 9. So it's up to you from how you want to work with this. You can actually either do 5 pi over 9, which was our first base, plus 6 pi over 9 twice, or we can just take our previous angle and then just add 6 pi over 9 to that. Again, 6 pi over 9 just being this that we're adding every single time. So it's up to you how you want to work with it. I'm just going to go from our previous angle, 11 pi over 9 plus 6 pi over 9 again, which again, this was our 2 pi over 3. So if we simplify, we get 4 cube root of 4 CIS, and that should give us 17 pi over 9. So there is our third angle there. So pretty basic example where we found the 3 cube roots to this standard, to this complex number in standard form. Now, really quickly, I just want to close this by actually graphing these 3 solutions for you, so you can see what they look like. So let me go in a little bit closer here. So we're going to get like 1, 2, 1, 2. Now, our first complex number, if we take this first complex number and we evaluate this, and I just punch these angles into a calculator and evaluate them and work and multiply them by the cube root of 4, what you find is that this is approximately negative 0.276 plus 1.563i. If I were to plot that complex number now on this complex plane, so our x value being negative 0.276 and our y value or imaginary number being 1.563, you would get a number right around there, okay? Now, what about the second root here? We said that this was we're going to say that this is approximately, and for the sake of time, I'm going to just give you the approximate value since I've already calculated these ahead of time. We get something like that. Now, what does that complex number look like? Well, negative 1.216 is our horizontal. Our vertical is just a little bit past that, right around there. So that's where that complex root goes. And let's do the final one, which was in green. This one right over here approximately turns out to be 1.492 minus 0.543i. I. And if I graph that complex number, positive 1.492, negative 0.453, right around there, these are our complex roots. And what do you notice about them? Geometrically, they form a triangle, which is very cool. That these complex roots would actually form a triangle, specifically because we were asked with finding the cube roots. So then you could think about, well, what type of shape would we get if we were asked with finding the fourth roots of a standard number or the sixth roots? You would get a square and, or rhombus, and a hexagon, respectively. So I encourage you to try this next problem. Try this one on your own. And just as a setup for you, just to make sure that you understand kind of how to approach this here, just keep in mind what you want to do here for this problem is understand that this number is the following. That 8 can be rewritten as a complex number as 8 plus 0i. Well, if that is the case, and that is our complex number, where this is 8 and our imaginary number is 0, that makes your life a lot easier when you need to find its distance from the origin. So r is simply equal to 8, and theta is simply equal to 0. So go ahead and try these next two examples on your own, where you are finding all the roots. For the second problem here, just to get you started, as a bit of a hint, understanding that this here would mean that x to the sixth is equal to negative 729. X, already just by taking the cube root of both of these sides, or excuse me, the sixth root of both of these sides, here, we can already get plus or minus 3i as two of the roots. There will be 4 more. So what we're effectively needing to do, and maybe I'm jumping a little bit too far ahead, is to understand that this x value can be rewritten as negative 729 plus 0i. And we're finding the sixth root of this. That is going to be how we're going to approach finding the roots there. So give those a go, and I've already uploaded the solutions to Classroom, so go ahead and check those and see if you can graph your roots as well.